All right, a wayward satellite of mass 1,500 kilograms has developed a highly elliptical orbit around the Earth. At its closest approach, called the perigee, it is just 500 kilometers above the Earth's surface. Its furthest point, the apogee, is 3,000 kilometers from the Earth's surface. The Earth has a mass of 6 times 10 to the 24 kilograms and a radius of 6.4 times 10 to the 6 meters. The gravitational field strength of the Earth is shown in the graph. So, part A, I'm going to leave the graph there for a minute. Calculate the change in potential energy of the satellite as it moves from the closest to the furthest point from the Earth. Okay, so it's labelled on our graph here, the perigee and the apogee. We need the area under that graph, and that gives us the work done per kilogram. So, we're going to have to count a lot of squares here. Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9.
1, 2, 3, 4, 5, 6, 7, 8, 9, 12. 12 times 4, 48. 49, 50.
I get 78. 74? Yeah. Look, as long as it's ballpark, so I put dots in every one of mine that I've counted. If you do something like that, again, the examiners reward good physics. So they just need to know how you've got your answer. Okay? If it's somewhere in that ballpark, you'll be fine. So I'm calling it 78. So each square is worth, what's each one worth? So it's 0.25 times 10 to the 6 underneath and 1 up the side. Oh, sorry, yep, 0.2, you're right. Yep. Okay, so each square is worth 2 times 10 to the 5 joules per kilogram. So we have 78 squares. We've got 78 times 2 times 10 to the 5. So 1.56 times 10 to the 7 per kilogram. That's our area under the graph. Joules per kilogram.
How did you get 0.02 times 10 to the 5?
2 times, oh, so it's just, so the area of that graph, so it's 1 times 0.2 times 10 to the 6, which is just 2 times. Yeah, so I've just shifted the, yeah. Okay, so it's joules per kilogram. We know we have 1,500 kilograms, so each kilogram of our satellite has that much energy working on it, so we need to multiply that by the mass of the satellite to get the total energy change.
What do you times to get 1.56?
So to get 1.56, I did 78 times 2 times 10 to the 5.
78 times 5.
And so if you multiply that amount of energy by the 1,500 kilograms of the satellite, we get 2.34 times 10 to the 10 joules. And that is its change in gravitational potential energy. Okay, so its total change in gravitational potential energy is 2.34 times 10 to the 10.
Why does it become 1.5? Because you times it by 7.
Sorry?
You times it by 7.
Okay, now, I'm not going to do the next bit as a full example because the bell's gone, but the satellite was moving with a speed of 15 kilometers per second at its closest point to the Earth. How fast was it moving at its furthest point? How would we go about working that out? Excellent. So at its furthest point, you can work out how much gravitational potential energy it has gained, which will be the same as the amount of kinetic energy it has lost. So work out the amount of kinetic energy it had at the start, work out its gravitational potential energy at the end, you'll have how much energy it has lost, and you can work out its speed. But we'll do that on Monday. Have a go at that last example over the week.